All right, last video here. Exponential functions and behavior. It's part A, and then we'll talk about equivalent expressions. So there are 4 types of end behavior for an exponential function. We have A is greater than 0 and B is greater than 1. So we're really dealing with this. Y equals A times B to the X. And then occasionally, I'll put it in a different color, because occasionally we have this plus K. I haven't talked about that enough. I do want to talk about that. It will be on your test. Okay. So if A is greater than 0, what does that mean? Well, it means that this A is positive. So A is a positive number, and B is greater than 1. So that means A is going to tell us where we start. Okay, so if A is a positive number, that's going to be where we start. Okay, so maybe here. Let's just say A is 2, all right? Let's just say for a second A is 2, that's greater than 0. And B is greater than 1, let's just say B is 1.2 or 1.3. Well, what is this going to mean? Because B is greater than 1, I'm going to have exponential growth. And it's going to grow like this. And what does that mean? The end behavior is going to approach, there's going to be a horizontal asymptote here at 0. And if I wanted to write that in limit notation, I would say the limit of whatever this is, f of x, it approaches 0. So the limit of, as x approaches negative infinity, f of x equals 0, because there's a horizontal asymptote here. But it's not actually that simple because of k. If I was adding something to this, it would just shift the function up. So instead, if k was equal to 2, no, let me just say k is equal to 3, it would shift this entire function up by 3. So this would be at 5 now. And the horizontal asymptote would happen at 3. And so this, well, why was it 0 in the last one? Because we weren't adding anything to it. So k was essentially 0. But really what's happening here is that we're approaching k. Whatever k is, that's what we'll approach on the left side. On the right side, we will approach, as this goes to positive infinity, where are we going? We're clearly going to positive infinity. So that's a little bit of a trick on these. Just be careful for k's, all right? Just think about if we're adding to this function, that's going to move it up or down. If k is negative, it's going to shift the function down. If k is positive, it'll shift the function up. All right, so let's talk about this one. We have A is greater than 0, and B is between 0 and 1. Okay, so A is positive. So again, I'm going to have a positive A. I'm just going to say here. But this time, B is, it's a decimal. And when we multiply by a decimal, we know we're getting smaller. So we're going to get exponential decay here. This is decay. The last one was growth. I didn't say that. Let me just note that now. Exponential decay. And so this is going to slowly go towards 0, just like last time, unless we had a k here that shifted the whole function up. So let's say k was 4. It would shift this whole function up 4. But if k was, I don't know, -2, it would shift the whole function down -2. And again, we're going to approach a horizontal asymptote at k. Blue, the k is 0. We don't have to write it. But red, it's 4. Green, it's -2. So if I want to be accurate about the limit notation here, I can say, well, the limit as x approaches negative infinity, the f of x is equal to, well, we're going towards negative infinity. But as we go towards positive infinity, f of x is going to approach k, whatever k is. If it's 4, it approaches 4. If it's -2, it approaches -2. If there is no k, then it just approaches 0, because think about it, y equals a times b to the x plus 0. You don't need to write plus 0. So essentially k is not there. All right, this time a is less than 0, so a is negative. That's another way to say this. Right? And b is greater than 1, so it's going to look something like this. Boom, boom. We're going to start in the negatives. and we're going to get more and more negative. So it's going to be like this. But again, I'm going to have this horizontal asymptote over here at 0 because this is assuming y equals a times b to the x plus 0, where k is 0. But if k, was 5, it would shift this up to 5. And I'd have a horizontal asymptote at 5. So just think about k on an exponential function. Something's going to approach k. So let's write our limit statement. The limit as x approaches negative infinity. What is the function approaching over here as we go this way? Well, it's approaching k, whatever k is. And the limit as the f of x, this is going to equal negative infinity. I don't know why I'm writing it this way. As x approaches positive infinity, we're going down forever. All right. Over here, a is less than 0 and b is a decimal. So again, boom, boom, a is in the negatives. So we're here, but this time we're getting closer and closer to 0. And again, unless this was k, that could shift it up, down, side, no, not side, up or down. So where are we approaching as we go this way? We're approaching k. But where are we approaching as we go this way? We're approaching negative infinity. So the limit as x approaches negative infinity, the f of x is equal to negative infinity. But the limit as x approaches positive infinity, the f of x approaches k. All right, so that's pretty theoretical. Let's make it a little bit more concrete. Write a limit statement for the following. I wish I would have added a k onto this. Maybe I should have, but I didn't. All right, we'll just talk about that. Well, the limit statement, okay. Well, what type of equation is this? This is exponential growth because I have a is greater than 0 and b is greater than 1. So it's going to be positive exponential growth. So it's going to look something like this. And there's no, k is 0 here. We're adding 0. So the limit as x approaches negative infinity, the f of x is equal to 0 because k is 0. But as we go towards positive infinity, the f of x is equal to positive infinity. All right, this time we have a that is less than 0, which means it's negative. And we have a b that is less than 1. 0.9999, it's very close to 1, but it is less than 1. So we're going to get something that looks like this. Going to start in the negatives and do exponential to k. Again, k is equal to 0. There's no number here. So as the limit as x approaches negative infinity, well, where is the g of x headed? It's also headed towards negative infinity, right? And the limit as x approaches positive infinity, the g of x is equal to k. And in this example, k is 0. All right. Oh, here we go. Here's one with k. Good job. All right. Write a limit statement for the following function. Negative 2 times 1.5. Okay, well, let's just, hopefully we're getting the hang of this. Start in the negatives, but we're growing. And I should do a better job. This asymptote is here because there is no k. So honestly, let me just redraw it because this is not a good representation. Should look something like that. Okay, but there's a horizontal asymptote here. So the limit as x approaches negative infinity. Where is this approaching? It's approaching again k, but k is 0. And the limit as x approaches positive infinity, where is this headed? The h of x is equal to negative infinity. All right, this one, I'm glad I wrote this question. We have a k of 5 right here. So that means we're going to be shifted up 5. So we have something like this. It's exponential growth starting at 2, multiplying by 3. So it should look something like that. But then we take this whole thing and we just drag it up 5. So it's really going to look like this. And it's going to approach k as we go to negative infinity. So let's write the limit statement. The limit as x approaches negative infinity, the j of x is going to equal 5, because k is 5. And the limit as x approaches positive infinity, well, where are we headed? We're headed towards positive infinity. All right, so that's exponential end behavior. What about exponential equivalent expressions? All right, so let me rewrite some of these. 3 times 2 to the 4th plus x. Knowing my laws of exponents, I could rewrite this as 3 times 2 to the 4th times 2 to the x. Right? Because when I'm adding exponents, really just multiplying those. So you rewrite this as 3 times 2 to the 4th is 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. So it's 3 times 16 times 2 to the x. Well, 3 times 16, that's what, 54? So we could rewrite this as 54 times 2 to the x. So these two equations are equivalent to each other. The same thing. All right, so this one we got interesting. 5 times 4 to the x times 2 to the x. So really, when okay, so I'm going to leave this 5b. 4 to the x times 2 to the x. For some reason, my brain is not wrapping its head around this quick. Let's just say that x was 2. So this would be 4 squared times 2 squared. So it'd be 16 times 4 is 64. Okay, so we can just, since they're the same base, we can just merge them. So this is going to be times 8 to the x. So we can do 5 times 8 to the x. These are the same thing. Did you guys notice my process there, though? Like, let me back out. I don't remember the law of exponent well enough, but I figured it out. How did I figure it out? I just said, okay, x is 2. What happens if x is 2? Well, if x is 2, I get 64 right here. Well, what else would give me 64? Just 8 squared. So that means I can just combine the bases. And now that I'm kind of remembering my laws of exponents, that makes sense. So this can be rewritten as 5 times 8 to the x. All right. Next one, we got a 7. When I've got a power here, well, I can kind of work backwards. What does the power mean? It really means to multiply the exponents. So this is really 3 squared to the x would be the same as, I could also write it like this, times 3 to the x. So now I have 7 times 9 times 3 to the x. 7 times 9 is 63, so we can also write this as 63 times 3 to the x. I kind of want to double check my math there. So why don't I check it with this? Why don't I say, what if x equals 2? Would these two expressions be equivalent? All right, well, let's substitute the first one. The first one would become 7 times 3 squared. And we would get 7 times, 3 squared is 9. 9 squared is 81. We get 81 times 7. So I actually don't think my math is correct. 81 times 7 is 567. And here we have 63 times, 9. 63 times 9. is 567. So my math is correct. So again, my law as exponents are kind of shaky. I haven't really explored these in a while, but I can figure it out. So when we see math, we really try to figure it out. This is correct because you can always check to see if your answer is correct with these because they're supposed to be equivalent. So if I substitute any number into x, I should get the same thing for both of those. All right. Now we're really testing me. Okay, so we have 2 times e to the x times 4 to the negative x. Okay, well, I know a negative exponent belongs in the wrong spot. So this is really 2 e to the x over 4 to the x, which e to the x over 4 to the x is really 2 to the x. This is really 2 times 2 to the x. All right, now I'm getting some rhythm. All right, I did not generate these problems, so that's why I'm solving them in real time. Okay, so this could be rewritten as 6 times 3 to the x divided by, so that really means subtraction or division. So 3 to the x over 3 squared. So 6, so really we're getting 6 times 3 to the x over 9. I could pull this out and we could write this as 2/3, because 6/9 equals 2/3 times 3 to the x. Okay. And again, if you wanted to check to see if this is legit, because I'm not 100% sure my math's perfect on these, why don't I just check? Why don't I say x equals 2? So, or maybe I should say x equals, oh, let's just say x equals 2. It should work for anything. Here we get 6 times 3 to the 2 minus 2. 6 times 3 to the 0. Anything to the 0 is 1, so this is just 6. Will I get 6 if I plug in a 2 here? Doesn't look like it. We get 2/3 times 3 squared. 3, oh yeah, I will. 3 squared is 9, so I get 2/3 times 9, which is 9 over 1. 18 over 3 is 6. Good, I'm right. So look how you can just check your work. All right, these are pretty difficult. Okay, 10 times 5 to the x over 25. Well, I mean, 10 over 25, I just want to simplify this. Divide by 5, I get 2/5. It's really 2/5 times 5 to the x. Do you want to check it? All right, let's check it. Might as well just keep making sure we're right. So let's just say x equals, I don't know, 2 is a pretty easy number to work with. So I don't want to keep choosing 2, but whatever. So substitute in a 2 here. 5 squared is 25. 25 times 10 is 250. Divided by 25 is 10. So will we get 10 here? So if I substitute in 2/5 times 5 squared, I get, sorry, it's loading. 5 squared is 50, so we get 2/5 times 50. 50 over 1, or 50 times, 2 times 50 is 100, divided by 5. Oh, sorry, I skipped. I messed that up. 5 squared is 25. 2 times 25 is 50. 50 divided by 5 is 10. I got the same answer for both expressions. All right. We've got 4 times 2 to the 3rd to the x. So I can say 4 times 2 to the 3rd times 2 to the x. 2 to the 3rd is 8. So we get 32 times 2 to the x. I'm going to just move along because this is becoming longer than it should. All right, this is about to get messy. I get 9 times 2 to the 2x times 2 to the 3rd. And so let's simplify. This is a good question. 2 to the third is 8. 9 times 2 to the 2x times 8. Now I'm going to combine these. Get 72 times 2 to the 2x. But I think we can take this even a step further. 2 to the 2x could be written as 72 times 2 to the 2 squared. I'm not actually sure I can simplify this anymore. 2 squared to the x. Oh, yeah, we can simplify that a little. What is 2 squared? It's 4. So this really can be written as 72 times 4 to the x. All right, good math. It's fun. I get to think. That's what math is, not memorizing processes. Thinking, oh my God, there's 16 of these? All right, I got to work a little faster. All right, we've got 8 times 6 to the x over 2 to the x. We're going to get 8 over 6 to the x divided by 2 to the x. That's going to be 3 to the x. So 8 times 3 to the x. Let's keep moving. This could be rewritten as 5 to the x times 5 squared. 3 times 5 to the x times 25. 3 times 25 is 75. So that's going to be written as 75 times 5 to the x. And just so we're aware, I mean, we're used to seeing it like this. Same thing. Okay. Oh, my goodness. All right, 12 times 27 to the x times 3 to the negative x. That 3 to the negative x belongs in the bottom, so this is really 12 times 27 to the x all over 3 to the x. 27 divided by 3 is 9, so this is really 12 times 9 to the x. All right, messy. This one's going to get messy again. We can rewrite this as 5 times 3 to the 3x over, because of subtraction, so I'm dividing, 3 to the 6th. 3 to the 6th. All right, 3 to the 6th. 3 times 3 is 27 times 27, which is 729. So we get 5 over 729 times 3 to the 3x. But 3 to the 3x can be rewritten as 3 to the third to the x. I'm just going to extrapolate this for a second. 3 to the third is 27, so this is 27 to the x. So this can be rewritten as 5 over 5 times 27 to the x divided by 729. All right, I might end up telling you guys not to do these last ones if you don't need to study. Feels like a little overkill, but nothing like getting really good at something. So this becomes 1/2 to the x, because 4 divided by 8 is 1/2. This is written as 18 times 1/2 to the x. All right. We get 20 times 16 to the x over 2 to the x, because that moves down. So we get 20 times 8 to the x. And this can be written as 7 times 4 to the x times 4 to the third. 4 to the third is 64, so this turns into 7 times 64, which is 448. Right, so 7 times 4 to the x times 448, times 64. It turns into 448 times 4 to the x. And last problem on the worksheet, and then I get to go to sleep. We've got oh, this is a good one. 24 times 10 to the x. Well, this can be rewritten as 10 squared. So we could really write this, if we wanted to, as 24 times 10 to the x minus 2. 24 times 10 to the x minus 2. Because why am I subtracting these? Because division with exponents turns into subtraction. All right, that's the last video. Good luck on your test, everyone.